Well, my name is not Ray, and no, I'm not on the moon indoor, but this lab is called May the Force Be With You. So in this lab, this is a two-part lab, which is guided inquiry in part 1, and then an open inquiry part 2, which is what I have set up here for you today, and what we'll go over and how do you set this up, and what are the safety precautions and the data collection and materials that you need. Now, obviously, because of this unprecedented time that we're in, I'm not in my normal lab setting, but I do have lab safety gear on. So with this lab, the mandatory, of course, of safety is your safety goggles. Gloves are not necessary. Obviously, probably due to a shortage, your students are not going to be able to have those if you're in a classroom setting. Now, because of possible virtual learning next year, I started thinking about this aspect and could you video this at your home? And there are home items sitting out and then non-home items. So this could be something that you could demo for the students and then have the data collection for them, and then they can take the data and then run the rest of the lab questions on their own, particular diagrams. So that's kind of what I'm going to model for you today so that you can think about this next year. If you're having to do a virtual lesson on this, your students can be engaged, they can explore, they can explain what is going on. There is an elaboration portion, and the beauty of this is that you can evaluate their knowledge with some of the lesson materials that are found in the unit that we have associated with May the Force. So let me go through with you. This, of course, meets the next generation science standards. This meets our Alabama course of study science standards, which I'm not going to elaborate upon. That's in our to-do reading material for you to look at. But I do want to go over with you some aspects of this. So in part 1 that I have laid out right here, your students are doing that don't flip your lid part of LTF materials, or if you're science and motion trained, it is the physical properties of substances. And that one is a great, fantastic one. But this lesson right here is great for when you're having to reteach with states of matter and do the just the physical properties. So I highly encourage you to use the science and motion version if you are science and motion trained of the bonding physical properties. It's fantastic. I use it in the fall when I'm on my bonding unit and introducing intermolecular forces. But this lab for me, and just me talking, is when I use this for when I'm in the states of matter. So they're, again, in part 1, they're going to go through and do that don't flip your lid. They're going to melt the wax, the sugar, the salt. And if you want to, you can demo the iodine crystals subliming from solid to gas. So that's a great component in the part 1. Also too, if you have your own class models, there are some questions associated with this, or you can use the PhET simulation model of molecule building or molecule basics if you don't have these models in your classroom. So I have 2 versions of the model built. I highly recommend that you have your students build both versions so that this is more of the ball and stick version, and this is the orbital version. And this, of course, is our friend the water. And that way they can kind of look at what is the difference between intra and intermolecular forces. So again, just as a brief intro, just a reminder, intramolecular force is covalent bonding. So in my hydrogen molecule right here, the covalent bond of the partially positive hydrogen is bonded to the partially negative oxygen. So therefore, this itself is covalently bonded. That's the intramolecular force. Now, when we're talking intermolecular forces, we're talking about 2 molecules. Between the 2 molecules, what are those forces? So this is a huge misconception with students, so really drive this home. So with these 2 models that I have right here, this is your preview for your students, your engage, if you will. I have it to where I'm going to align my hydrogen of one molecule that again is partially positive to my oxygen on the unshared pairs here on my oxygen, which is partially negative. And that distance in between the two creates that intermolecular force of hydrogen bonding. And as we know with our students, that when we teach this to them, that the hydrogen of one molecule will bond to either the oxygen of the other molecule, to a fluorine of another molecule, or a nitrogen of another molecule, to create that strong intermolecular force of a hydrogen bond, which is actually a type of dipole bonding, if you want to know. So that's a great little engage aspect that I love about this reteaching in this part 1. And here's also another kit that I have that I got from, I think this was from back in Science Innovations. That's where I got this one. So this is a great little small kit if you can't afford the Flynn kits. And I have one right here. Just want to show you that so that you can kind of see this is the inorganic, organic. This is my teacher model set. And I have a classroom set for my students. I have 7. But you can look this up on the Flynn catalog and be able to see this material pretty nicely. So that's the intro to part 1, and now we'll dive into part 2. On part 2, the series of materials that you're going to need for this demo / engage, explore, explain, and elaborate lesson is a series of materials. Now, I like to put in my classroom, in my lab, a cup that is labeled, and of course I'm at my house, so I just have styrofoam cups, but a cup with either the name written on the table, because we all know our students, they stick solutions in different places, don't put it back correctly, but if it's clearly labeled for them, they won't mess up. So this is just kind of some teacher tips that I've learned over the years. So I've labeled it, of course, my water. I've got my isopropyl alcohol, my acetone, which is my fancy nail polish remover. And then I brought today my butanol and a hexane. Now this hexane, it could be any alkane. If you notice right here, the students, you can kind of, if you have hexane, that's great. If you have pentane, just any alkane is gonna work. So of course in my classroom, in my lab, I literally just grabbed and ran out the door with some hexane, knowing that I may not be able to come back. So these are the materials. Also too, you can either have, I have ethyl alcohol. If you want to use ethanol in the lab, you can have that ethanol, or you can substitute out the butanol with the ethanol. It's just whatever you would like to test. So sometimes I kind of set that off as like a engage, or like, okay, compare and contrast the ethanol to the butanol. And we'll talk about that with our bonding later in our elaborate session when we discuss this lab at the end. So this is my setup. I've got filter paper, I've got rubber bands. Now my rubber bands, these rubber bands are just what I had around the house. The orthodontic rubber bands that you can get from Flynn or science companies that are small in diameter, those typically are the best ones because you're just not having to use a whole lot of rubber band wrapping around. Now, I'm going to demonstrate the setup on this digital vernier probeware. This is something that you also can be able to buy. Now, don't forget, with your resources and your materials, you are going to be getting a classroom set of the LabQuest, Vernier LabQuest, and I'll talk about the setup on that in just a minute. Or if you would like, if your Wi-Fi is excellent and you have extra money, instructional fee money or science money, that you can purchase this. This is a digital thermometer that you can have. It's a wide range thermometer that can actually be uploaded to the Vernier LabQuest software on any electronic device. So the students can collect the data and send it to their cell phones. Depending upon your cell phone policy, depending upon your classroom needs, this is also a great tool. So obviously it comes with your USB cord. You can use to plug them to a computer or phone, whatever electronic device. Another added bonus. So basically, take filter paper and you're just gonna gently wrap it around. And again, I would demo this and model this for your students. That way they kind of have an understanding. I mean, not all of them need this, but again, if your students are like mine, sometimes they just need a little visual demo of what to do. So I kind of wrap it around my temperature probe, the stainless steel temperature probe, and I tie my rubber band around the filter paper. Now the problem with the filter paper rubber band setup is you can't leave this setup all day. So if you have multiple sections of your chemistry labs, you can't really leave this on here, even though the alcohol, the alkanes, and even the water is going to evaporate by the next time the next class comes in. You really can't leave it on here because over time that rubber band is going to disintegrate. So yes, you have to take it apart every time. Now, so that's how to set up your filter paper. Notice it's kind of loose, but that's okay because eventually we're going to set it up on our standing thermometer, as you can see right here. So I taped down thermometers on the table, my vernier temperature probes. Now, because I had access to 2 temperature probes with a vernier, I had multiple temp probes, and that's something else that you might want to think about. Time frame. The data collection goes very quickly if you're having 2 per vernier probe. There's multiple ways that you could do this in your lab setting, and depending upon if you're a period class or a block classroom setting. If you're a period classroom setting and you want quick data collection with your students, literally less than 20 minutes, this data collection will occur. So you set up your 2 temp probes. It's easily marked channel 1 and channel 2. As you can see here, it's clearly color coded. So channel 1 is red and channel 2 is blue. And if your students forget, you can also write on the masking tape or tape on your table of which one is temp probe 1 and temp probe 2. Now, this time of year when you're doing this lab, I don't set up lab materials for them. I make them set it up. The only thing I set up when I'm doing this prep is the solutions, and I have a solution collection site from which they share from. So in my lab setting, I would have a station on this side of the table and a station on this side of the table as well, so they can share the common solutions. So you're not having to make up so many areas of setups of chemicals, and it's not going to go to waste. Also too, with these chems, with the exception of water, you're going to have to wait until right before class time to pour, just pipette out a little bit or pour a little bit into the test tube for them to collect from. The reason again is it'll evaporate and get fumes in your lab setting. Depending upon your filtration of your lab, it's just not safe. So again, I just kind of overfilled it today, but you can really fill it just a little bit, just has to get onto that filter paper. So this is kind of how I set it up in the classroom. Tell the students they can tape it down, provide tape for them, but this aspect here, the students will do for themselves. So this is a great setup in terms of either a partner pair of 2 or even with 3 students. You can have one student getting temp probe 1 ready, the temp probe 2 ready, and then the third person will hit the play collection button. So therefore they can just record the data. Even a 4th person, depending upon time, depending upon your class size, can be the recorder for this experiment. And then you can change it out a little bit at each station if you want. Make sure they rotate if they want that experience, or just keep the jobs the same. And ideally you want to keep the jobs the same. So that's my setup. That's how I use it in my lab setting. We'll transition in just a second into actual data collection. All right, so in our data collection, the students are going to, and you, are going to obviously write down the first 2 temperatures. So this would be called our initial temperature, and what we're going to measure is our final temperature. Because we're doing evaporation, the temperature is going to drop, and that's what we want the students to see, even on a hot day like this outside. So if you're not familiar with the LabQuest, the vernier, I can talk to you about how to set that up, but basically it's pretty simple. Here's your power cord. If it's charged, you don't need the power cord. Here's your power button. I've got my kickstands right here that I popped open so that it'll stand up and kind of be able to, where I can see it a little bit better. And then I plugged in my temperatures probes in port 1 and 2, and it's labeled on the side, the channels. Channel 1, channel 2, and there's even a channel 3. Notice there's that USB that you can download the data on a computer device. And then of course it rotates and you can kind of see that. like that. Sometimes it does that when I rotate it around. That way you can kind of see it better. So it's going to automatically collect data. However, you can push the play button and it'll give you time frame and sample size. The good thing about this lab design is that we don't care about sample size. We don't care about duration. I mean, you can set it up if you want to for a time of no more than 5 minutes, or if they have a cell phone, if they have their Apple Watch, or if they have a laptop, a one-to-one school systems, they can just set up a timer and you can tell them, okay, don't let it run for more than 5 minutes. We just want to see what the highest temperature is and the lowest temperature. So that's the beauty of this. It goes pretty quick. In terms of when the students say, hey, the temperature went back up again, then you know you're done. So literally, it's very simple, very easy. You don't have to hit play. It automatically collects the data. So what I'm starting with is my alkane, and I've taken it off of let's get that on there. And I've soaked my filter paper. Stick that back in there. Now obviously if I had my pipettes, I would just squirt the pipettes on there. And notice the data is already being collected with my alkane. I'm going to tape this to where my filter paper is hanging off the table, so no residual heat from the table is going to affect that filter paper. So as you can see in channel 1, the temperature is already changing. Now on my temp probe 2, I'm putting in my butanol, and I'm going to pour that on there. I'm outside, good times, had by all, and there we go. And so my temperature is already changing. So if you notice, my temperature 1 now is dropping to 23.7. My temperature 2 is dropping, it's 25.6. So again, I'm going to let this run for a few minutes. I'll give you the final data collection points. We're going to wait to see if they level off. And the reason why I started with the alkane and the butanol is because they evaporate faster. I kind of go from the fastest to the slowest. That way the student's kind of like, oh, wait a minute. But I was just doing it in a hurry. I kind of went from left to right, right to left. You can see that the students will do the same. And tell them it doesn't really matter which two they begin with or which substance they start with. They just need to pick a point, make sure they know what substance they're measuring, and have that maximum temperature and that minimum temperature. So we keep seeing the data changing. Notice maybe that channel 1, it's still dropping, so we're going to wait just a few more minutes. And remember, my alkane is hexane, so that's gonna take a little bit longer to evaporate than like a pentane. Notice I'm still dropping in temperature. That's fantastic. That's what we want. Temperature is still dropping. While the temperature is still dropping, I'm going to also give you another little tip in terms of that my cameraman, my father, today reminded me that you can get those hair ties, those tiny little hair ties for braids, or that girls use. Perfect. You can also use those if you don't have a lot of money and you don't want to spend a lot of money on those Flynn fancy orthodontic rubber bands. Those work just as well, and they're super cheap. You can get them at any dollar store or Walmart. Temperatures went back up. So my lowest temperature, if you saw that on channel 1, was 19, and then my channel 2 is 24.0. So I'm going to call it for these first two. So with the beauty of videoing and being able to stop and start. Once I've shown you how to set it up, we're now going to run our next run. And I didn't touch the LabQuest, but notice my ports jump back up to about 28.3 and 28.5. Students, when they see this, will say, oh, well, something's wrong. They're not exactly the same. And I always talk about, it's okay, that's calibration. So each thermometer is calibrated a little differently. As long as it's in the same range, plus or minus a point, 10th place, it's okay. It's fine for this exercise. All right, so now we're going to run acetone and isopropyl alcohol, or aka rubbing alcohol. So again, I've got my acetone here. Now the tape, let me talk about that as well. Watch your students, remind your students. I'm an evil teacher. I really don't tell them because and I'm just going to pour that on. There we go. I don't tell them about the tape, and here's the reason why. Some students will tape it on the probe, and that will affect their temperature data. So I'm kind of evil that way. So notice your temperature 1 is dropping already. It's already at 22, went from 28. So even if they're slow like I am, because I'm old, and do one temperature at a time, it's good. It is all good. And I don't want this to slide off, so I'm just pouring that on there. Since these are household items, it's really okay. And we're outside. So now I've got my acetone, my isopropyl alcohol. Notice my rubbing alcohol is now dropping, 25.4. So again, that's an aspect that if your kids tape the tape to the stainless steel probe, that can affect their temperature data collection. So we're just going to watch this, see how low the temperature will drop. Now, rubbing alcohol typically takes approximately 1.5 to 2 minutes for it to finally evaporate. Okay, your acetone, pretty dang on quick. So acetone is probably one of the fastest ones, along with your hexane, your alkanes really. So we should now have 21.1. I'll come back and give you your lowest and highest temperatures again, but you can just kind of see the data as we're watching it. So really only about 2 minutes is necessary for these 2 data collection points. Let's see if we're stabilizing. Looks like our channel 1 is stabilizing. It's still dropping. Our channel 2 probe. Yeah. So they've stabilized. We're going to call it end result. All right, so for our last data collection, notice I've done this in 3 rounds. I'm going to do water, and then I'm going to show you what the ethyl alcohol looks like compared to the butanol. So again, I'm going to slide this down and just pour some water on my filter paper. Done. I'm outside. Beauty. Notice I was started at 38 degrees. It's going to evaporate a little bit, but remember, water is going to take forever to evaporate, like 20 minutes max. So now this is the this is the ethyl alcohol. The ethanol that I'm using is denatured. If you notice, the temperature is going to drop. It's going to take a little slower. So my water is evaporating. It's not as quickly as my other substances. The alcohol on average, whether it be methanol, ethanol, methanol is approximately 40 seconds. Ethanol is going to be about 60 seconds, so about a minute. Notice we're kind of running side by side now. Dropping down to 27. Water is still dropping. Woohoo! Kids are like in competition with each other. I'm winning. I'm winning. Alcohol's winning. Now they're running almost simultaneously at the same time. Still dropping, but now notice who's taking the lead in terms of the drop. Notice the ethanol or ethyl alcohol is now surpassing the water. Not by much. Water's still catching up, still evaporating. It's almost like you can see those water molecules turning from a liquid to a gas. This is another misconception that students believe, that they think that the bonds will break. It is not the intramolecular forces, but it's the intermolecular forces, which are separating. Again, ethanol still in the lead. While they're doing their data collection, they're going to, with this lab setup, this design, it has them create their own data table. So I kind of like that a lot in terms of this. In other lab setups and other lab write-ups, the LTF version, the Science and Motion version that we do in the fall, it kind of provides a data table for them. So remember, when this lesson is supposed to occur, this is in the spring, third 9 weeks into the fourth 9 weeks, and you want at this point the students to be engaged in developing their own data table design, creating a qualitative and a quantitative. So this is what I really love about this lab, is that there is quantitative data that has to be collected, but there's also qualitative, the observations, the smells, remind them of their senses. As we're watching our last set around, obviously in a true lab setting, you would have closed-toed shoes. I chose for the cute shoes today and being hot and outside, so the fun of teacher training, right? From home. So notice your alcohol pretty much is stabilized at 22.5. Your water, let's watch it for just a second or two more. Dropped a little bit more. Once it starts holding at a temperature for about a second or two, if you're in a rush for time, if the bell's about to ring, what have you, in your sequence, you can just kind of call it. So if it's been a minute, 2 minutes, you can just tell them at that time frame, all right, collect data for 2 minutes, record the temperature change, because you're still going to have that good piece of data from your highest temperature before evaporation and your lowest temperature of after evaporation. And notice the two-point difference in the temperature collection, as we see now with the water with the red temperature probe and the ethyl alcohol with the blue temperature probe. All right, and we're going to call it our last temperature set.